In this video, we will discuss the wave-like nature of matter by discussing the de Broglie wavelength. In this video, we're going to extend our discussion of wave-particle duality from light to matter. We will discuss how to solve for the wavelength of matter by using the formula for the de Broglie wavelength. So while frequently we talk about light being a wave and a particle, we can also do that with matter. But we can't use the same equation since that doesn't account for the differences between light and matter. For this, we need to use the equation for the de Broglie wavelength. This is determined by Planck's constant over momentum. We know that momentum is equal to mass times velocity, so this will also give us h over mv. It's also worth remembering that kinetic energy is related to 1/2 mv squared, since you'll often use this equation to find the velocity during problem solving in this section. First, we'll do this for a calcium atom. We will fill into the de Broglie wavelength equation. We know that the mass from the periodic table of a calcium atom, but that mass isn't in the right units. We need to switch from the grams per mole that we get from the periodic table into kilograms per atom. We can do this using our standard conversions for the metric units and Avogadro's number. From here, we can fill back into the de Broglie wavelength equation. For V, though, we have to do another problem, or another piece of a problem. We need to use the kinetic energy formula to go from kinetic energy to velocity. Once we have the velocity, this can go into the de Broglie wavelength formula. And now we have all of our knowns, and we can solve for a de Broglie wavelength. Once all of the units cancel, we see that it's in meters. We started with 3 significant figures, and all of the numbers we filled in kept at least 3 significant figures. So we have 3 significant figures at the end. Now I want to propose a question. If matter has waves, then how come we can't see this for everyday objects? We see a car or a baseball or a snowflake, etc., as a particle without any sort of wave-like properties. So why is that? Let's use the de Broglie wavelength equation to think about this. Let's take the values for a baseball and fill in to find out the wavelength of a baseball. If we fill in the value of a baseball moving around 27 meters per second, we can get the wavelength of the baseball. Notice how small that is. It is way, way, way smaller than the baseball itself. So much smaller that it would have no impact on how we treat the baseball. And this is the case for all macroscopic matter. It's why wave-particle duality is only talked about for extremely small things, like electrons and protons. We now know that not only does light have wave-particle duality, but so does matter. Though this really only makes a difference for extremely small matter like electrons and protons and such. We can calculate the wavelength for any particle by using the equation for the de Broglie wavelength. It's just oftentimes these wave-like properties don't make a difference to the matter.